Hi everybody, this is Jose Abel. This time with a quick video regarding one particular element in the class of quadrilateral elements, this time the second order quadrilateral element. This finite element is characterized by having 9 nodes displayed as in the picture here, and we have the ability of having curved sides in this element. And the usual node numberings for this is first the edges 0, 1, 2, 3. Then we move on to the mid sides 4, 5, 6, 7, and then finally the middle node there in the final element. So the shape functions associated with this element are the 9 shape functions that you see here. These are b-quadratic polynomials, so you'll see that they're second order in one of the two natural or parent coordinates, chi and eta. And either chi or eta, you see that these are second order polynomials, but because they're or biquadratic, that means that in a diagonal direction it's actually a fourth order polynomial. So because it's a multiplication of two second order polynomials. Anyway, these shape functions have the property of being 1 at each of the nodes. So for example, n0 is 1 at node 0, and then 0 at all the other nodes. That gives the basis or the polynomial set of functions or the shape functions the property of interpolation. That means that we can specify or interpolate the geometry of the element and then later the solution just using the nodal values. And this function is complete. They can specify any b-quadratic polynomial, and in particular they could specify a polynomial which is linear in these two variables, and that means it can represent any reached body motion. So here's a little Python module that computes the value of the shape functions given chi and eta, and it returns all the shape functions in a list. So if you pass in here a single value and a single value, you'll get single values out. But if you pass vectors in, you can get vector or array values out. So we can use this to visualize the shape functions. So this is a neat little display of the shape functions. Let's see if we can enlarge here. So here for the first node, which is located in the parent domain in the bottom left corner, you can see that the value of the shape function is 1, and then maybe you can see that for the other nodes it's going to be 0. Now for the second function, you see that's also the case, and for the third function and for the fourth function, so that covers the corners. And then we move on to the edges. You can see that this looks like a parabola in that direction, and then in the other sides and nodes it's going to be of a value of equal to 0. In this case, we have the number 5 node, if I'm not mistaken, so the 5 one belongs to that edge, and then the top edge right here, and then the left side. And finally, the middle node is this so-called bubble function, which is 0 in all the edges, but then has a value of 1 in between. This is a b-quadratic function, this bubble function. So with this polynomial basis of functions, I can combine them, create linear combinations of these functions to basically interpolate the displacement field and also the geometry inside of the element. So this is a useful way to looking at the shape function. Now, the Quad9 actually bilinear mapping. Let's quickly edit this in the Python notebook, the Jupyter notebook. The shape functions are used to interpolate the geometry using basically the chi eta coordinates or get mapped into x coordinates by multiplying the shape functions with their respective nodal coordinates. And this is the same for the y coordinates. So this is basically an Iso-Parametric mapping from the parent domain in chi eta coordinates to xy coordinates. We can compute this conveniently using this small function that calls the shape function module that we specified before. So this one up here gets called down here in the interpolate geometry, given values of the chi and the eta basically arrays. So for example, there's some hidden functions here I'm not showing in this module, but here's one that can show you the element mapping. So let's start with a regular square. This is just a square located in, I'll just show you. So on the left-hand side is the parent domain. So you can see it goes from -1 to 1 in chi, and -1 to 1 in eta, so that's the parent. Here's the location of a point I've singled out in the plotting function. And all the blue lines are equal eta value, and all the red lines are equal chi value. So you can see in the mapped domain, this one is going to 0 to 2, and then from 0 to 2. So it's basically just a translation of the original or the parent element. And I did that by specifying the coordinates of the nodes. So the first 4 coordinates correspond to the nodes on the side. You can see 0, 0, 2, 0, 2, 2, 0, 2, and then the next are the midpoints. It's 1, 0, 2, 1, and then 1, 2, and 0, 1, and finally the middle node is 1, 1. So that's the mapping. And then I can goof around with this. In the next step, I'll just let's start with the regular element. I think this should be the one. So this is the original element, and now we can move one of the sides. So let's take the middle node here and move it a little bit. Let's just nudge it a wee bit, and we can see how the isoparametric mapping of the domain occurs, right? So I move this element, and this distorts all these lines of iso or equal chi value and eta value into these curvy lines, which are actually a biquadratic mapping, and it also drags the point that I'm specifying here in the domain to this other point over here. And you can see here, like in real time, what's up with the mapping. We'll talk about the Jacobian in a second, but first of all, you can see that you can make this mapping not onto, so basically not bijective, or basically if given a value of chi and eta, is there a unique value of this? You can see that as I move this point all the way over there, for example, you can see that these lines start to overlap with each other. I can do a very extreme version. Let's go over there all the way to 1.8, and you'll see now that the values actually go beyond the element and out. So in these areas over here, the mapping is already non-unique because there's two like patches of chi eta values that map onto a given chi eta, so two patches or yeah. What I mean is for any given value of x and y, you'll get two values of chi and eta that, or more, that correspond to that value. So this is not great, but this is what happens, and in this case we'll see further on that the Jacobian is going to warn us of this of this situation. So let's put it back to its original place for our comfort. And then let's do a little bit more. So for example, it's fun to analyze what you can do with the mid side. So let's go for the second mid side. So it should be this one at 1 to 1. Yes, to 1. So if I start moving, for example, this node towards the side, you can see what happens with the stretching of the lines to the right. But you can also see something which is not so intuitive, is that the other lines towards the left-hand side get moved towards the left, and I can stretch that a little bit more, and eventually, if you do that enough, you'll get these to overlap too. So if I go all the way to 5, maybe, you start seeing some problems, some heavy distortions in the edges over here, and overlapping to this side. So that gives you a sense of how far you can stretch that side. Not good. And then we can move it upwards, so we can start moving this way. You see the stretching that goes on. Let's do a little bit more over here. 1.3. You see the elements start shrinking, and then they start stretching on the other side, and you can see the other side here, down here. You get these curvatures going on. Let's go to 1.5. 1.5 is the limit, and this is where when you start to have zero Jacobian at that corner. So if I push back to that side, you'll start to see a negative Jacobian or non-invertible isoparametric mapping. Okay, so let's show this. To compute the Jacobian matrix, there's some sort of problem there, but that should. What did I do? What did I do? Can I undo? Undo. Control C, undo. 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 I don't know what happened. So, okay, so I just erased everything over there. It doesn't matter. We can compute the Jacobian determinant. I had some formulas. I got completely lost over there. Sorry. To compute it, so the Jacobian determinant is defined, or the Jacobian matrix is defined as the partial derivatives of the x and y coordinates to the psi and eta coordinates. And in this formulation, you just compute it with as the summation of the, and this is set up over here for the quad 4 element, but it's analogous for the quad 9 element. Let me just quickly replace those indices. That's driving my OCD crazy. But here I should extend this all the way to N8 and then add the additional rows for each of the other nodes that we have. Anyway, you can use this formula to compute the Jacobian, and then you invert the Jacobian to compute the derivatives of the shape functions with respect to the xy coordinates, which are needed as part of the formulation of the final element. So given the chi eta, or the apparent domain derivatives of the final element, you can compute the xy derivatives of the shape functions using the inverse of the Jacobian. So here we have a little function that will plot this Jacobian over the element, given for the element I showed before. So we can take a look at what's going on. So in this case, what we did is we moved this node up, and we can see these elements down here are stretched, so they should have a bigger Jacobian, basically. And then these ones over here should go to 0 or negative. And this is exactly what we're seeing in this mapping right here. We see a negative Jacobian over here, and we see a Jacobian over 1 over here, which basically means that as we take differential elements from the parent domain, the Jacobian tells you how much you have to multiply this area over here to get this area over here. That's the basic intuition. So you see smaller than 1 Jacobians over here and larger than 1 Jacobian over this side. Just because the element is, they have the same initial area. So you'll see that on average it looks like 1, so because the element has the same area, but you need to undercompensate for this side and overcompensate for that other side. So this is a little bit fun. Let's go over here, let's bring the node back to 0, and you'll see that the Jacobian just flats out to 1, which is fun. You can see these color differences are just color differences due to basically being the color scale being limited to a very narrow range. But as I move the central node, let's move it as we did before a little bit. You can see what happens to the Jacobian. This side gets compressed, which means it should have a less than 1 Jacobian, and this other side should have a greater than 1 Jacobian, and we'll see what happens to these other sides. We'll rerun this cell over here. Woo! And that's what it looks like. It's like a funky wave. Yeah, so I hope this helps you out understand a little bit of how this quad 9 element works. Other than this, you just need to integrate it as you would with any other finite element. Just a proper Gaussian quadrature rule, and do your quadrature, and you're ready to go. I'll have another video on Gaussian quadratures if you're interested in that. Until then, I'll see you guys next time.